Hello everyone. So today I wanted to go over some nice properties of a matrix, and it really depends on what kind of matrix we're talking about. So the first nice property a matrix has is orthogonality. So orthogonality in relation to another matrix. So let's say that we have a matrix Aij, which again, since we're writing this in Einstein's summation notation, which is basically like saying the matrix A, or in this case we'll call it A1 because we're trying to prove or show the orthogonality between two matrices. So now let's say I have another matrix A K J. Now the reason why this index is repeating is because we're going to multiply these. So now this will be a second matrix. So we call this A2. So if we multiply or sum over the index j in this matrices, what we will find, so let's do a sum over j. That, again, written in Einstein's summation notation, we can get rid of the sum. So we have this. And this is going to be equal to the Kronecker delta of ik. Now, what does that mean? What this means is that each row in the matrix is matrix 1 is orthogonal to the one in matrix 2. So the only way that this is going to be equal to 1, so the only way that this is going to be equal to 1 is if I is equal to k, in which case it just kind of means that they're the same matrix. But otherwise, it's going to be equal to 0 if I is not equal to k. So this also is the same case for columns, right? So here we did it for rows, which is our second index, but let's say now we do it a sum over I, where now we have Aij and Aik. So you can see now instead of summing over j, we're summing over I, which again in Einstein's summation would be Aij, Aik, and this would be equal to delta of jk this time, where if j is equal to k, this is 1. If j is not equal to k, this is 0. So this is a nice property of some matrices. Now let's try to show another property. So another cool property of a matrix is if the determinant of a matrix A is equal to 1. There's no real reason yet why this is a nice property. I haven't explained anything about that, but it is just a nice property to have. A determinant, the best way I found to calculate it is, let's say I have a matrix 1, 1, 3 going across, and let's say 2, 8, 1, 0, 3, 0, right? So let's say I have this matrix, and I'm going to call this A. This matrix, to find its determinant, right? The determinant may not be 1 in this case, but I'm just showing you how to calculate the determinant. So the determinant of this will start from the top left and will multiply all the way down to the bottom right. So in this case, we have 1 times 1 times 3. To this we will add, we'll move over one step in the column, and we will multiply again the same exact way. We'll go diagonally downwards. But you can see that when we go diagonally downwards, there isn't a third term here. But the third term will just be this one repeated, right? So if we repeat the first two columns, we get 1, 0, 3, 2, 1, 0. Now we can see that we can now multiply this, and this basically gets repeated over here. So We'll differentiate this. Okay, so we have 2 times 1 times 3. 2 times 1 times 3. The last one we have 8 times 0 times 0. We don't even need to write that. Next thing, we're going to go the opposite way. So now we start from here and we go backwards, but instead of adding, we subtract it. So subtracting 2 times 0 times 3. 2 times 0 is already 0. 0 times 3 is 0, so we don't need to write that. Next one, 1 times 1 times 0. Okay, that's also 0, so we're not going to write that either. And then the last one, we have 8 times 1 times 3. So we have 8 times 1, which is 8, times 3, which is 24. So now we have this plus this minus this, which gives us 3 plus 6 minus 24, which is 9 minus 24, which I am just going to quickly assume is 15. And it is. Okay, let's just say it's 15. So now that we have the determinant of A here as 15, usually a nice property of some sort of matrix is if the determinant is 1, as we wrote here. So in this case, sure, the determinant is 15, but it's not 1. So we want to try to find a matrix which has a determinant 1, because then it can have nice properties. So last property, which is kind of important, is the transpose or the inverse. Now, the reason why we mentioned these first two properties is that if it satisfies the first condition, where 1, it is orthogonal to another matrix, and 2, it has a determinant of 1, then what we can say as our third property is that an inverse of that type of matrix is equal to the transpose of that matrix, right? So we're essentially just using these first two properties as a condition to satisfy this last condition. And usually the transpose of a matrix isn't the same as an inverse of a matrix. We can go over how to find an inverse of a matrix later. And a transpose of a matrix, again, it's not always the same as an inverse. But in this case, if this satisfies the first two conditions, we're good.